Ever stop and think about how we can possibly predict the weather? Or design brand new drugs from scratch? Or even simulate the entire universe inside a computer? Well, it takes a staggering amount of computing power, literally thousands of processors all pulling in the same direction. So how on earth do they coordinate? Okay, let's pull back the curtain on the secret language that makes it all possible.
To get a sense of the scale here, imagine you have a truly massive problem. Let's say solving a giant matrix equation. If you gave this monster task to a really good, top-of-the-line desktop PC, it would sit there and churn away for about 231 days. That's right, over 7 months of non-stop work.
Obviously, they're not just using a slightly beefier version of what's on your desk. They have a completely different playbook. So what's the secret? How do they get this unbelievable speed up? That's the big question we're going to tackle right now.
So here's our game plan. We'll start with a hard physical limit that forced a big change in computing. Then we'll look at the clever solution that engineers came up with. After that, we'll learn the actual language they invented to make it all work, see some of its cool features, and finally, put it all together to see how today's supercomputers operate.
All right, first up, hitting the power wall. You really have to get this part to understand everything that comes next. This is the reason we had to completely rethink how we build the world's fastest machines. See, for decades, we had this beautiful, simple rule called Dennard scaling. It was like magic. Every time we shrunk the transistors on a chip, they got faster and they used less power. It was the perfect win-win. But around 2005, that magic formula just stopped working. The transistors got so tiny that they started leaking electricity and generating a crazy amount of heat. The bottom line is, we hit a literal physical wall, a power wall. The old strategy of just making a single processor, a single brain, think faster and faster, it just wasn't an option anymore. We simply couldn't get rid of the heat fast enough. We needed a whole new approach.
And that brings us right to our second section, the many-mind solution. The new idea was actually pretty simple, at least in concept. If you can't make one brain think faster, why not use thousands of brains all at once?
And this slide just nails the difference. On the left, that's the old way. One really fast processor doing everything one step at a time. Simple, but slow. On the right is parallel processing. You chop up the big problem into little pieces and you give each piece to its own processor. It is so much faster, but, and this is the big catch, it requires coordination. And here we are at the absolute core problem of modern supercomputing. It's a huge deal. All these thousands of processors, they aren't looking at the same piece of paper. In fact, they have no idea what the others are doing. You see, each processor or process has its own completely private memory, its own little world. It can't see its neighbor's memory at all. The analogy of being in different soundproof rooms is perfect. You can have a brilliant expert in one room, but they can't collaborate with the expert next door if they can't talk to each other. They need a communication system. Which leads us to the star of the show, MPI. This is the incredibly elegant solution that lets all those isolated experts in their soundproof rooms work together like a perfectly coordinated team. So what is MPI exactly? Well, it's not a programming language like Python. Think of it more as a library, a standardized set of tools you can use in other languages. And its whole job is to provide a way for processes to send and receive messages. It's the universal language, the Lingua Franca that everyone agrees to speak. It's what turns a giant collection of separate computers into one massive supercomputer. At its core, MPI communication really breaks down into two main flavors. You've got point-to-point, which is just what it sounds like. Process A needs to send a specific message directly to process B. It's a private chat. Then you have collectives. This is for when you need to talk to a whole group at once, like a broadcast announcement or a company-wide meeting. Now, MPI is way more than just sending simple messages back and forth. Let's peek at a couple of the more advanced ways these processors can talk, which is where the real power comes in. This is a fantastic example of a really common collective operation. So imagine each processor has done some work and now has a single number, its little piece of the answer. A reduce operation gathers all those numbers from every single process, sends them to one designated root process, and then combines them. Maybe it adds them all up or finds the maximum value. It reduces thousands of little answers down to one big, meaningful result. And then you've got even cleverer stuff, like one-sided communication. This is really cool.
It lets one process directly reach into another process's memory to either drop off some data, a put, or grab some data, a get, without the other process having to stop what it's doing. It's like leaving a note on a bulletin board instead of having to call a meeting. For some problems, this is way, way more efficient.
Okay, so let's bring this all home in our final section and see how all these ideas fit together in a real modern supercomputer. It's actually a team of teams.
First, we have to zoom in on a single node. You can think of a node as just one really powerful self-contained computer. Now, inside this one box, you have a bunch of workers, CPU cores, maybe some GPUs, and the key thing is they all share the same memory. They can all see the same whiteboard, so they can talk to each other super fast using their own special languages like OpenMP or CUDA.
But a supercomputer isn't just one node. Of course not. It's thousands of these nodes, all linked together with a super fast network. And, you guessed it, we're right back to our original problem. Each one of those nodes is in its own soundproof room. The memory in node number 1 is completely separate from the memory in node number 2.
And this is the punchline. This is the modern hybrid model. It's a two-level system. Inside each node, where memory is shared, you use tools like OpenMP and CUDA for blazing fast teamwork. But to communicate between the nodes across that network, that's where MPI comes in. It's the language that connects all the individual teams, making them act like one giant cohesive brain.
This quote just says it all, doesn't it? At the end of the day, MPI is the essential glue. Without it, you wouldn't have a supercomputer. You'd just have a warehouse full of very powerful, very lonely computers that can't talk to each other.
So we went from a problem that takes 231 days down to just a few hours. That's the power of parallel computing, and MPI is the engine that drives it. But as we dream of solving even bigger problems, like simulating the entire human brain, it leaves you with a pretty exciting question, doesn't it? What comes after MPI? What will that next great communication breakthrough look like?